Hello, my name is Rich Thuma. I'm with Crawford Murphy and Tilley, and I'm going to be talking to you today about the development of an airfield master plan for McMurdo Station, Antarctica. So first, to give you an idea of what I'll be talking about, I'm going to pass along some general information about Antarctica so you can understand the continent. I'll go into more detail about the air operations on Antarctica, and then get into some details about how we analyze the runway headings that were ideal for the location, and talk about development of the airfield configuration, how the runways and taxiways and parking areas fit together, and then share with you the final configuration recommendation and some conclusions about the effort. So one general theme about how about the airfield in Antarctica is that things are similar but different. And what I mean by that is the airfield has all the same components of an airfield you might find in the United States or anywhere else on land. It has runways, taxiways, aprons, lighting systems, nav aids, all those sorts of things. And here's an example, an air passenger terminal. It's a simple building. The main difference between this building and any other building on a land-based airfield is that it's on skis instead of on wheels. And if you look inside that building, you see it's got 4 walls, a roof, it has some windows, a heating system, and some chairs on the inside. But the real difference is the environment that this air passenger terminal is sitting inside, and how extreme that environment can be. And when a door is left open just a slight bit, and the wind is blowing and snow is blowing, that room can be changed into a whole different world. So keep that kind of similar but different theme in mind as we go through this airfield master plan development. So Antarctica, it's a place you don't get to visit very often. I've been fortunate to visit there 3 times, and it's a whole different world. It's the 5th largest continent. It's nearly 100% covered in ice, and it's really the harshest environment on the planet, the coldest, the windiest, the driest. It is a world unto itself. For a frame of reference here, Antarctica is a big place. It's bigger than the continental United States. And so because of those distances and the poor environment, air travel is just about the only option for getting materials moved around the continent. So what is the U.S. doing down there? The U.S. is only doing science as well as all the other nations that have facilities in Antarctica. The entire continent is dedicated to science. No commercial development, no military, nothing like that. So the U.S. has 3 stations, one at Palmer Station, which is on this peninsula of Antarctica that kind of lines up with the southern tip of South America. If you can imagine, Chile is right up in here. We have a station at the South Pole, and so that's sitting up on about 10,000 feet of ice on top of the continent underneath. So it's a high elevation station, extremely cold, extremely windy. And then the largest station is McMurdo Station here on the Ross Ice Shelf. It's actually on a small island right next to the Ross Ice Shelf. And it is the point closest to the pole that can be reached by water, by ship, each year. Here's an aerial view of McMurdo Station. And it's what I might describe as or what I can imagine maybe an Atlantic mining camp or mining village might look like. It's gravel roads everywhere, a lot of industrial buildings, a lot of storage areas, both outdoor storage. You have fuel storage here. You have a big galley here, a place to feed everyone. You have dormitories up the hill here, lots of warehouses. And everything that you see here supports operations in one building, this Crary Science Building. And this is where all the scientists are housed, where their offices are. They have laboratories there, all sorts of different facilities. But you can see this is a big, expansive area supporting one small facility. And that's because the logistical challenges of doing anything in Antarctica are so difficult that it's about a 50-to-1 ratio between support staff and scientists, principal investigators. So it's a very unique environment and requires a lot of logistics to support everything. And that's where the air operations come in. The facilities, all the stations in Antarctica are supported by air. McMurdo gets one ship per year. Well, maybe it's two ships, one cargo ship and one fuel ship per year that come in. But primarily it's all air. So at McMurdo Station, you have 3 different airfield facilities. You have an annual sea ice runway. You have Williams Field Skiway. And skiway is different than a runway in that it's only used by ski-equipped aircraft. And you have Pegasus Glacial Ice Runway, which is out here, and that can be used by wheeled aircraft. The other runways on the continent include a skiway at the South Pole, so only aircraft equipped with skis can fly between McMurdo Station and the South Pole, and that occurs almost daily, actually. And that's to move people, food, fuel, other equipment to the South Pole to support the science that is going on the South Pole. And then there are also seasonal field camps, and these are places where scientists, maybe geologists or climate scientists might go to set up experiments, and the air services there are just done on natural terrain using ski-equipped aircraft. So let's get into more detail about the different airfield facilities at McMurdo Station, because that's where this study was focused. McMurdo has a sea ice runway that has been in use since 1957, and I say it's been in use since 57. Well, the concept of a sea ice runway has been in use since 57, but that sea ice runway actually melts every year and is refrozen every year, and each time is built in a slightly different location from the previous year. It's used from about October 1st to December 1st each year, and the time that it's used is completely dependent on the thickness of the ice and the temperature of the ice. And using that information, you can determine how much weight it can support. At the end of the sea ice runway season, and the last aircraft leaves, and then all the equipment that's out there on the sea ice has to get moved to one of 2 other fields, either Williams Field or Pegasus Field. So everything's on skis, and a dozer or a snowcat is hooked up to it and pulled off the ice before it melts. So the Williams Field Skiway has been in use since about 1960. It's on the Ross Ice Shelf, so it's on a big, thick, 100-foot thick layer of ice, but it's in an area relatively close to Mount Erebus, the volcano, right on Ross Island, where there's heavy snow accumulation. So they have feet and feet and feet of snow piled up on top of the glacial ice. And that snow has not been compacted enough to support wheeled aircraft. So this field is only used by ski-equipped aircraft. It could be used year-round, but it's traditionally has been only used from about the 1st of December to the 25th of December, or 25th of February each season. And then Pegasus Glacial Ice Runway. This is the 3rd field, and it has only been in operation since about 93. At that time, the U.S. Antarctic program decided they needed greater airlift capability to bring in more and larger size equipment, so they started flying aircraft that could operate on wheels to McMurdo. And to do that, they needed to be on some thick ice, and so they decided, well, let's grade off, clear off the glacial ice surface and operate on that, because it's 100 feet of ice. It's plenty strong enough to support any aircraft you can put on it. And they did that for almost 10 years, and then they were having trouble with the clear glacial ice absorbing the sunlight, focusing the sun's rays during the 24 hours of sunlight, and creating melt spots on the surface. So in 2002, they decided to put a snow cap on the glacial ice. And so this is a compacted snow layer that's only 2 to 4 inches thick, but because it is white instead of clear, it reflects a lot more light and helps preserve the glacial ice underneath and keep it from melting. Like Williams Field, this Pegasus glacial ice runway is generally used between the 1st of December and the 25th of February. And it is used by wheeled aircraft, always for wheeled aircraft. Here's a close-up picture of that white ice surface. You can see it just looks like compacted snow that, a roadway that's been driven on, but it is very hard and dry. So when aircraft touch down, they actually leave rubber on the surface, and that creates a problem for maintenance because that black rubber absorbs sunlight and starts melting the snow. And so after every touchdown, the maintenance crews have to go out there and blade off the black rubber, get it removed and pushed off to the side so that you don't end up with any melting problems. So in development of this airfield master plan, we had some objectives, and the idea was to consolidate these 3 different airfield operations that had traditionally been the sea ice runway, Williams Field, and Pegasus glacial ice into one operation, one airfield that could operate year-round, and that would reduce costs and reduce redundancy of resources. So the requirements were to support C-17 aircraft pictured here, LC-130 aircraft using either skis or wheels. They can operate in either mode. Occasionally a 757 or a 319 fly into the continent from New Zealand or Australia. There's other smaller aircraft like the DC-3s, Twin Otters, and helicopter that also operate on the airfield. And the new airfield would also need to meet the payload and passenger capacity requirements that are presently happening today, as well as allow for future expansion. So this shows on a map the relative location of these different airfields to McMurdo Station and why, how things have operated historically. So the sea ice runway is up very close to McMurdo Station. It's only 1 to 2 miles from the land where all the buildings are. So that's very convenient. It'd be great if they could operate on this runway every year, year-round, but the ice melts, so that can't happen. Williams Field is only about 7 miles from McMurdo Station, so it's a snow road across the glacial ice and relatively short transit. So that's somewhat convenient, I would say, to McMurdo Station. Pegasus Airfield is quite a distance away from McMurdo. It's 14 miles one way, this long road all the way around out to Pegasus, and that presents a problem. So they tried an experiment, kind of a 2-year experiment in 2010 and 2011, and they operated the sea ice runway for a short time, and then they did not operate Williams Field, but they built a skiway out at Pegasus and moved all the operations out to here and operated there from 1st of December until early March. And it went reasonably well, but the roadway and the distance traveled became a bit of a problem. But they still wanted, with this study, to decide, was this really the best configuration for a long-term airfield facility? From the air, this is what the layout of Pegasus looked like in the 2010 and 2011 years. This blue area here is an outline of the glacial ice runway used for wheeled aircraft. This gray rectangle over here is the skiway. You have a C-17 parking ramp here and taxiway, a short taxiway here connecting the skiway to the purple area is the aircraft parking apron for LC-130s. You also had fuel pits, or I'm sorry, fuel tanks over in this area that would resupply the LC-130 aircraft. And this green area here is a snow berm that during the non-flying season, all the buildings and equipment are put up on top of, so that drifts form behind them, not on top of them. There's a number of complications with this airfield master plan that occur here but not in other locations. And those have to do with the winds, the soot plume created from LC-130s, snow accumulation versus snow ablation. You have different types of markings, lightings, nav aids, and snow grooming and surface maintenance is a real key factor. I'll go into detail on some of these. First of all, prevailing winds versus storm winds. After looking at the historical data of winds at the site at Pegasus, we found that the prevailing winds blew in one direction. So the winds blew most commonly out of the east, so along kind of the 8-0 direction. But the storm winds, when the winds blew the hardest, they were blowing out of the south, out of the 1-8 or the 1-9 direction. And those storm winds end up being a major factor because you can get significant drifting that takes a lot of time to clear snow away if you don't set up your buildings and equipment properly to put those drifts where you want them. So you have to consider both the storm and the prevailing winds. Soot created by LC-130s is also a problem. The aircraft for the LC-130 is a relatively dirty engine, and you end up with deposits on the snow from the exhaust. This is an area where they parked an LC-130, did an engine run-up test, and you end up with this stain on the snow. Well, that's going to absorb sunlight and lead to melting. So we had to be concerned when we orient the skiway relative to the runway that the skiway that's predominantly used by the LC-130s that isn't set up so that a soot plume forms kind of right off the departure area on top of the glacial ice runway. We needed separation between the skiway and the runway. Snow accumulation versus snow ablation. This is kind of focusing in, zooming in the aerial here to show you where Pegasus is relative to McMurdo Station here on the land. You can see this dash line here. It's kind of the difference between the gray and the white, and this is all clear glacial ice. This is snow here, and because we want a snow cap on Pegasus, we need some snow, but we don't want so much snow that we're constantly pushing snow around just to get it out of the way and off of the runway. And the complication here is that the ice shelf is continuously moving this direction in about at a rate of about 20 feet per year. So if you build it here, eventually it's going to end up over here in the ablation zone. And they're dealing with that now and actually have moved the airfield a bit to accommodate or account for that movement. As I mentioned, snow grooming and surface maintenance is a continuous chore. That white ice cap has to be maintained, smoothed out, compacted, and there's a lot of equipment, specialized equipment that's used on the airfield just for that purpose. This picture right here showing the hole through the ice gives a good example of the difference between the snow ice cap, the very white surface, and the glacial ice underneath. So let's jump into the runway skiway heading analysis. For this approach, we looked at all weather station data recorded since 1990, and we first evaluated the existing configuration, which has the Pegasus runways on a 1533 heading and the skiway is on a 1028 heading. With those headings and a 15-knot crosswind, doing a traditional wind rose analysis, you end up with 98.43% coverage, which is excellent. It's really very good, but we wanted to know, is that really the optimum? So we looked at all the wind data, trying to determine the best runway direction, And to do that, we excluded, when we looked at the skiway, we excluded the storm winds out of that. I'll dig into that a little bit more here in a second. We went through a lot of different configurations trying to come up with the optimal configuration. First of all, on the runway, we tried a lot of different headings. I'm kind of rotating through these. And you can see that the 95.68 with a 15-knot crosswind at 95.68% coverage provides the best optimal heading for the glacial ice runway. Now, on the skiway, it was a little different because essentially, if you just were trying to determine the skiway, you would end up with the same heading as the runway. But we wanted to, I guess we recognize the skiway as kind of their secondary runway. It's used as the runway itself will be used as the backup runway. And whenever there's bad weather and the storms are coming in, they'll be operating on the runway. So we wanted to operate something that was more aligned to the prevailing winds. And first we excluded all winds greater than 28 knots and looked at a 10-knot crosswind limit, and that put us on an 826 heading. And then we also did the same analysis, but we excluded winds greater than 22 knots, and that also put us on an 826 heading. So that's ultimately the configuration that we came up with was the best. If you combine them both together, we ended up with a 98.74% coverage, which is slightly better than the 98.43%, well above the minimum 95% coverage that is desired. All right, so after we had our runway headings, we started looking at the airfield configuration in general, the other facilities that connect the runways to the parking apron. And we, as a starting point, looked at the existing airfield that was in use during that 2010-2011 seasons. And you can see here we have the runway, the skiway, and then some parking aprons, fueling areas, building areas, all attached to it. So we had to put all these other facilities into a new configuration. We first tried a town south configuration, and this was a very efficient layout from the standpoint of reducing the amount of area required to be groomed. Everything is quite close together. We have short taxiways and a very compact layout. Unfortunately, the storm winds put all drifting on the north side of facilities, and that's ultimately what threw out this configuration is all your buildings and everything were going to be on this side. That would throw drifts into the aircraft parking aprons, and that ultimately was the downfall of this arrangement. So then we shifted to a town north arrangement. It's really not all that different than the existing configuration. Here we have our 1836 for the runway and 826 for the skiway. I'm sorry, yeah, 826 for the skiway. And probably the biggest difference here is that we ended up with recommending an island arrangement for the fuel tanks so that aircraft could be serviced, filled with fuel on all sides of this fuel tank area rather than just on one side as it is in the current. And from there we went to the final configuration, which only involved changing to 2 rows of aircraft parking positions for the LC-130s. And we found that this configuration was able to reduce the overall groomed area from 212 acres in the present condition down to 195 acres in the town north configuration. So about an 8% reduction, providing basically the same capabilities, but it did provide more positions for fueling aircraft. We have a couple 3D renderings of the recommended airfield configuration, and you can see here this is these are the fuel tanks right here. Here's all the buildings. Here's the air traffic control tower. You have C-17s parked out here, LC-130s all through here. This is another view of it. Here's the fuel tanks again. There's the air traffic control tower. Have the runway out here, accessible for the C-17s. And then last thing we wanted to check is that we had visibility from the air traffic control tower to the approaches of each end of the runways. And this was the most demanding or obstructed, I guess, approach. But you can see if you look at that little green, gray dot right there, that's an LC-130 on approach to the skiway. And you can see by putting the camera inside the air traffic control tower, even though this tower is much shorter than you might have on a regular airfield, we do have an unobstructed view out to that approach. So some conclusions about this study are that it's really critical to get input and participation with all stakeholders that that use an airfield, and that was a large number of people for this this study. We had to do a somewhat non-traditional wind analysis to determine the correct heading for both the runway and the skiway. We've found that it was possible to reduce the airfield footprint, the groomed area, while expanding capacity. And probably one of the biggest conclusions of this process is that by going through this planning process, we really help better define the requirements for snow and ice airfields and help them refine the documents, the criteria documents that define what how a snow or ice airfield needs to be built and configured. So if you have any questions, I would ask you to reach out to me via email, and I look forward to hearing from you. Thanks.